Have you ever heard of gravitational waves? It's a relatively new phenomenon in science, but it's actually not that new, because Einstein predicted them in his general theory of relativity. But before we can dive into gravitational waves, we must first understand gravity.
According to Einstein, the fabric of spacetime is like a mesh that can be stretched or compressed in every direction. A large mass such as a star or planet causes the warping of this spacetime.
This bend or curve can be compared to a large marble in the center of a bowl. The marble creates a bend or curve in spacetime, causing other objects to gravitate towards it.
This is the phenomenon discovered by Newton known as gravity.
Because of gravity, what goes up must come down. But more importantly, gravity is what causes the Earth to stay in orbit around the Sun.
Gravity is what prompted Einstein to predict that if two giant masses such as black holes collided, they would cause ripples in the fabric of spacetime. This is similar to the ripple effect in water.
As it turns out, Einstein was on the right track. Wait! This is my dog Einstein, but I'm talking about Albert Einstein.
The first gravitational wave ever detected came from the collision of two black holes. Gravitational waves are also formed from supernovae, rotating neutron stars, binaries, or inflation. So what happens when a gravitational wave reaches the Earth? Well, the Earth is stretched similar to the way a balloon is stretched vertically and horizontally. A laser interferometer can be used to detect these shifts on Earth. It consists of a beam splitter and one mirror on each end. A laser is shot through the beam splitter, and the two beams travel down arms of equal length. They are then reflected by the mirrors and meet back at the beam splitter. The beams create an interference pattern, which is displayed on the photodetector. Now, if the lasers travel exactly the same distance, they should create a type of interference called destructive interference. This means the light waves from the two lasers cancel out, creating no light. As a gravitational wave passes by, one arm is shortened and the other is lengthened. As a result, the interference pattern changes. This is called constructive interference, and in this case, the light beams do not cancel out as easily. This causes a beam of light on the photodetector, which tells scientists that they have in fact detected a gravitational wave.
One huge problem was that gravitational waves are so tiny that a machine had to be built that was sensitive enough to detect these tiny shifts on the Earth.
Another obstacle was that there is so much background noise on Earth that could mimic the results of a gravitational wave. The detector created had to be able to isolate gravitational waves coming only from space. So scientists created LIGO, which stands for Laser Interferometer Gravitational Wave Observatory.
LIGO is a massive interferometer made up of two 4-kilometer arms. Its enormous size plays an important role in the sensitivity of interference patterns. In addition, vacuums ensure the laser beams are pure, and seismic isolation systems suspend mirrors so that even the tiniest vibrations do not affect them, like me jumping up and down.
These systems remove background noise, but how can scientists be so sure that they've detected a gravitational wave? There are two observatories, one in Washington and one in Louisiana. If the two detectors collect precisely the same data at the same time, then scientists can be certain that they have in fact detected a gravitational wave.
So, scientists detected a minuscule change in the size of the Earth. What's the big deal?
Well, for one thing, Einstein's theory is finally confirmed. But more importantly, scientists have discovered a new way to see the cosmos, or a sixth sense if you will. We have always relied on light to see things, but light can only travel so far. Gravitational waves are not blocked or slowed down by anything, so we now have a new way to detect cosmological events beyond our field of vision. The detection of these waves can be compared to a deaf person gaining his or her hearing. But most of all, the detection of these waves is so revolutionary because we could possibly detect gravitational waves from the Big Bang, opening up answers to our long-asked questions about the universe.